Hello students, in this video we will see another example of deriving a electrical analogous system for a given mechanical system. This time we will be taking a mechanical rotational system and apply torque voltage and torque current analogies so that we get a electrical analogous circuit. So here is an example of mechanical rotational system, and we have got to write the differential equation governing it and then convert it into an electrical system using torque voltage and torque current analogies. So first job is to find the nodes. There are three nodes here: node 1, node 2 and node 3. For the first node 1, there are three elements connected. One is J1, B1 and another one is K1. The torque is applied. So you will write the equation as J1 into d square theta 1 by dt square. So we have taken the displacement, angular displacement of node 1 as theta 1, node 2 as theta 2 and node 3 as theta 3. So it is J1 into d square theta 1 by dt square plus B1 is connected between node 1 and node 2. So it is d theta 1 by dt minus d theta 2 by dt. So that is for the second element B1. Third element K1, it is K1 into theta 1 minus theta 2 is equal to torque T. So now as usual, let us convert the equation which is written in terms of displacement to velocity. So the angular velocity d theta 1 by dt will be equal to omega 1. That is the angular velocity is written or given the name omega 1. So d square theta 1 by dt square is now written as d omega 1 by dt. D theta 1 by dt is written as omega 1. Theta 1 is written as integral of omega 1. So this is how you convert the equation to in terms of velocity. Now let's write the node 2 equation. Node 2 equation J2 into straightly in terms of omega d omega 2 by dt plus B1 is connected between node 2 and node 1. So it is omega 2 minus omega 1, and K1 is connected between node 2 and node 1. So it is integral of omega 2 minus omega 1 into dt. So another element B2 is there. B2 is connected between node 2 and node 3. So it is B2 into omega 2 minus omega 3 is equal to 0 because no torque is there. And the last equation is uh, three elements are there: J3, B2 and K3. For these two elements, it is only the displacement theta 3 or the velocity omega 3. For this B2, it will be omega 3 minus omega 2. So you can see here B2 omega 3 minus omega 2 plus K3 into integral of omega 3 dt is equal to 0. So now to get the torque voltage circuit or the torque current circuit, the corresponding elements has to be used. So let us substitute torque voltage analogous elements. In torque voltage analogous elements, the torque is replaced by voltage. Here I am given voltage E of t, and the velocity, angular velocities are replaced by currents, mass by L1, damper by R1 and spring by 1 by C1. So likewise you get all the three equations. After getting all the three equations, you have to draw a circuit which satisfies these three equations. So here is the circuit which satisfies the three equations. So there are three currents I1, I2, I3. So we have taken three loops I1, loop currents I1, I2, I3. If element is shared between two currents, then it comes in common. See here R1 and C1 are common between I1 and I2. So R1 and C1 comes in common, and then R2 is common between I3 and I2. So R2 is kept common between these two loops, and the voltage is given only to the first loop. I'll teach you a small shortcut also, as I said earlier in the force voltage. You can see here three nodes, so three loops. J1 is exclusively to loop 1, whereas this K1 and B1 are connected between node 1 and node 2. So here in the circuit also you can see that the equivalent for mass, that is the inductor, is only for this loop 1, whereas the C and R are in common between the loop 1 and loop 2. Similarly, here except for J2, this B2 is common between the node 2 and node 3, and these two elements are common between node 2 and node 1. Same thing you can view in the circuit also, except for this L2. Here two elements are common between node 1, loop 1 and loop 2, and R2 is common between loop 3 and loop 2. And these two, that is J3 and K3, are exclusively for node 3. So you can see here inductor and capacitor are only for the loop 3. There are two ways. One is you can draw the circuit by looking into these three equations keenly. The other way of doing is like you can see how many nodes are there, convert that to that many number of loops, how many elements are connected to a node 1, that many elements have to be connected here to the loop 1, and you have to take care of how many elements are common between node 1 and node 2. So you have to place those elements between common between loop 1 and loop 2 here. Similarly, to write torque current equivalent equations, we have to apply torque current equivalent elements for the node 1, node 2, node 3 differential equations of mechanical rotational system. So here the mass will be replaced by capacitor, damper by 1 by R, spring by 1 by L, and angular velocity by voltage, and torque by current. So similar replacements you should do it for the node 2 and node 3 also, so that you get these three equations. Now we have to draw a circuit which satisfies these three equations. So there are two or three voltages, V1, V2 and V3, three voltages. So select three nodes, 1, 2, 3. Okay. Elements which are common between node 1 and node 2, that is a V1 and V2, should be shared like this. See, you can see here between 1 and 2 there is a resistor. Between 1 and 2 there is a inductor L1. So we have taken R1 and L1 between V1 and V2, and current is only given to the node 1. And here also you can see between V2 and V3 there is an element R2. So this is actually R2. Likewise, you complete the entire circuit. The circuit will satisfy these three equations. So you can straightly come from the mechanical rotational system also. So you see here three nodes, 1, 2, 3. So in the circuit also we have seen three nodes, 1, 2, 3, and uh, equivalent element for J1, that is capacitor, was connected only to node 1. The equivalent elements for spring and damper, that is the inductor and the resistor, was connected between node 1 and node 2. And again, the equivalent element for J2 is C2 in torque current. So that was connected only to node 2, that is node 2 and ground. Whereas this B2, which was connected between node 2 and node 3, so the equivalent element is R2, which was connected between node 2 and node 3. And here also you can see that the equivalent for J3 is a capacitor C3, which will be connected purely to node 3, and the equivalent for K3 is your inductor L3, that will also be connected only to the node 3. You can see all these things here. So whatever I was telling orally, you can see that. So these three capacitors only to this nodes. It is not a common between two nodes. It's actually connected between node and the ground. The common elements were connected between the corresponding nodes. This is actually R2. So like this, you draw a circuit which satisfies these three equations. Actually, this first equation is node 1 equation, second equation is node 2 equation, and third one is the node 3 equation. Using KCL, if you write three node equations for this circuit, you will land up in writing all these three equations.